Hello all, in this video I am going to teach you the 4 different stages of C compilation process in detail. So before starting, let me ask you this question. What do you mean by compilation? The process of converting English like looking high level source code into CPU understandable low level binary code is called as compilation. So the tool that actually performs this compilation or conversion is called as a compiler. So the input given to a compiler is the source code, which is called as hello.c, and the output that we get after completing the compilation operation is an executable file called as a.out or hello.exe. So a.out is an executable file on Unix machines and hello.exe is an executable file on Windows machines, right? So in order to convert this high level source code into low level binary code, the compiler has to perform 4 operations stage by stage, right? So what are those stages or what are those operations? Stage 1, it performs pre-processing. Stage 2, it performs actual compilation. Stage 3, it performs assembling, and stage 4, it performs linking. Only after the compiler does all these 4 operations, we get the final executable output a.out. The input given to this compiler to the pre-processing during the pre-processing stage is the source file hello.c. Therefore, when an input hello.c is given to the pre-processing stage, it does the pre-processing activity and then it gives the output to the actual compilation stage. After performing the actual compilation, the output is given to the assembly stage. After the assembling stage, after performing the assembling activity, the output is given to the linking stage, and finally linker will do its job and finally give us our executable output a.out, right? Now, let me explain each step one by one, right? So before that, pre-processing is done by a tool called as C preprocessor. Actual compilation is done by a tool called as C compiler proper. Assembling is done by a tool called as assembler, and linking is done by a tool called as linker, right? Now, what happens during pre-processing stage? During the pre-processing stage, the C preprocessor will go through this entire source code, that is the C source code, line by line by line, in search of a line that starts with a symbol hash. And if the preprocessor during the pre-processing stage, okay, if while going through this entire source code, if it finds any line that starts with a symbol hash, then it can understand or it will realize or it will understand that that particular line must be taken care or must be evaluated by the preprocessor itself. It means in a source code, any line that starts with a symbol hash will be taken care by the preprocessor during the pre-processing stage itself. Now, what will it do? So in my source code, which I am showing it to you on the screen over here, okay, in this source code, we have only one line that starts from hash, that starts with a symbol hash. So the moment the preprocessor sees this line with a symbol hash, okay, it understands that it has to go and do some activity. So what is that activity is told by the next word, okay, after your hash symbol, which is nothing but include in this example, right? The moment the preprocessor sees that there is a word include, it understands that it has to go in search of a file called as stdio.h that is placed in between your angle brackets, okay, to a specific directory location. Okay, it goes to a specific directory location where all your standard header files are kept. Okay, it tries to find this stdio.h among those group of header files. It opens the header file. Once it finds this stdio.h, it opens the header file, okay, reads the content of that header file. It will come back to the source code. It will replace this line with the contents that it actually read from stdio.h, and after replacing those contents in this file will become an expanded source code. That is, a source code which contains hardly 6 to 7 lines of code will now become a very big code, an expanded source code, right? So which we call it as hello.i. It's called as hello.i. okay, it's an intermediate code, okay, a code which we get after pre-processing stage is basically after textual replacement. We call it as textual replacement, okay, because okay, pre-processor would go in search of this file stdio.h, find that file, read the contents of that file, come back to the source code, will remove this line from here, and in place of this line, whatever it had read from this file stdio.h, those contents would be put over here. It would be replaced in this particular file, right? And this source file, the original source file, that is hello.c, will become an expanded source code, okay? And that is basically the preprocessor does, and the output of the pre-processing stage is hello.i. Now let me just revisit that using this slide. Okay, the first step, that is the pre-processing stage, is taken care by the preprocessor. All lines starting with hash symbol is interpreted. It means any line that is starting from hash would be taken care by the preprocessor during the preprocessor stage. So when I mean that it would be taken care by the preprocessor, it means that any line that starts with hash would be interpreted or evaluated by the preprocessor. It is the preprocessor's job to evaluate the lines that starts with hash, right? Now next is the source code gets expanded due to textual replacement, as I said. Okay, so the contents of stdio.h would be replaced in the source code. Okay, that is, it would replace this line completely. It would remove this preprocessor directive line, and in place of this line the contents of stdio.h would be actually placed, and the code would become an expanded source code. The output which I showed you over here in the earlier slide, it is called as hello.i. So hello.i is nothing but an expanded version of hello.c after performing the textual replacement. Okay, now if suppose you want to find these hello.i, if you want to see how it actually works in practical, then you will have to use the command cc, and you will have to give it an option called as minus capital E along with the file name, and redirect it to a file called as hello.i. Okay, and this is the output that we get after performing the pre-processing stage. So I would call it as hello.i. So let me show this practically to you. Okay, so let me use this command and try to show you what happens to hello.c after the pre-processing stage. So let me open my terminal. Right, so as you can see, we have a file hello.c. This is the same program that I showed you on the screen here. Okay, a little while ago, this is the same program, right? This is the same source code, right? Now let me come back. Okay, as you can see, we have 1 2 3 4 5 6 7 lines of code here. Okay, and this is the original source code. So after the pre-processing stage, what you must notice is that this line would be replaced with the contents of stdio.h. What the contents that are there in stdio.h would be fetched by the preprocessor, and this entire line would be replaced with the code that is there in stdio.h, and this becomes an expanded source code that is called as hello.i, which I am going to show you now. Okay, so I am repeating certain things again and again so that it goes and sits in your head for a very long time. Okay, now okay, so let me compile that using the tool. Okay, that is when, let me use this tool. Okay, cc minus capital E hello.c, and I'm redirecting it to hello.i. Okay, and when I press an enter key, okay, you can see now there is extra file that is created that is called as hello.i. Right, now if I open that file, okay, hello.i, you can see that the entire source code has been replaced by something else, right? Some content, some textual replacement has happened, and this textual replacement has happened because preprocessor fetches the contents of the file stdio.h and has been replaced over here, right? So if you can see the original source code, okay, if you can see here, give me a moment, 1567. Okay, when you can see over here, this is the original source code that you had written. You can see it's at the bottom, right? And top of it, you had earlier had hash include stdio.h in .c file, but now it is not there. It means that line has been replaced by the contents of stdio.h. So this is basically the output of the pre-processing stage performed by the preprocessor, right? But now you must understand that this is not the compiled file. It is only the pre-processed file. Still, it has not been compiled. Hello.c is not been compiled. It is only pre-processed. So you can see hello.c was the original file, and the output now we got was hello.i. Okay. Now let us proceed to the next stage of compilation process. So once the pre-processing has happened, we get the output as hello.i, and this hello.i is actually given as input to the C compiler proper, whose duty is to do the actual compilation. So what happens during actual compilation is that this hello.i will be taken by the C compiler proper. It will check for all the syntax errors, or it checks if entire syntax of the source code is right or wrong. If it finds any problem with the syntax written in the source code, if there is any, say for example, if there is any semicolon missing, if there is any open brace missing, or if there is any close brace missing, or is there any a wrongly typed keyword or something like that, then the actual compilation will stop there. It means the C compiler proper will not proceed with the compilation. Okay, that is the next step. It doesn't proceed further. It stops the process here itself, and it throws an error saying that no boss, I will not be able to proceed further because there is a lot of syntax errors, right? This is what happens during your actual compilation. It means the actual compilation step is the stage where all your errors are checked, okay, especially your syntax errors are checked, and only if there is no syntax error, only if the source code is free of errors, it would proceed to the next stage, else it would stop over here and throw an error. Okay, so let me just recall that using a slide. the actual compilation stage, that is the second stage, right? So the compiler proper takes care of this actual compilation stage, checks for valid syntax of the C language, throws error if syntax used is wrong, okay, else converts source code into assembly code. It means if suppose it did not find any error, and if if it thinks that hello.i is absolutely right, it has no errors, then hello.i would be converted into an assembly file called as hello.s. So hello.s is a file that is generated by the C compiler proper after performing the actual compilation. So that is the output. So input to the C compiler proper during the actual compilation stage is hello.i, and this hello.i will be converted to hello.s. So what does this hello.s contain? This hello.s contains assembly instructions or CPU instructions, the mnemonics for the binary code, right? Say if suppose you have done your 8085 or 8086 programming, you can recall you would have used some CPU instructions like add instruction, push instruction, or pop instruction, and so on and so forth, right? So this is basically your assembly instruction that would be generated after your actual compilation stage performed by your C compiler proper. Okay, so if you want to see that the .s file, that is hello.s file, which I just mentioned over here, then you will have to use the command, okay, cc minus capital S, and give that input the pre-processing, the output of pre-processing stage, that is hello.i, that is the expanded source code, as input to C compiler proper, right? So hello.i, if you use this command, then you will actually the C compiler proper will convert this expanded source code into your assembly code, which looks like this. So let me call this as hello.s. So this is the output file format that you basically get after performing your actual compilation. Okay, so let us try this out practically. So the command used is cc minus capital S, and now we are giving the input as hello.i to the actual compiler, that is the C compiler proper, to generate hello.s, right? Now let us go and see that practically. Okay, so as you can see, we have hello.i over here. Now let me use the command cc minus capital S and give the input as hello.i. Hello.i is the pre-processed file. Okay, so when I press an enter key, and then if I see, yes, as you can see that earlier there was only hello.c and hello.i. Now I have generated another file called as hello.s, which is nothing but the assembly file. Okay, so if I run that code, when I open that code and see what I open that file, okay, we can actually see all the assembly instructions generated. Can you see this? You can see all the assembly instructions generated over here, and this is the assembly code for the actual source code that you have written in hello.c, right? Now, this is hello.s, which is nothing but the output of the actual compilation stage, but the CPU cannot understand these instructions. It is only human understandable, so the CPU will not understand all this. CPU can only understand the binary code, which are in zeros and ones. So we need another tool which is called as assembler, and it comes in the third stage during the assembling stage. So during the third stage, what happens is that the assembler will read this assembly code and convert this into another file called as hello.o. Okay, and this is called as object code. Okay, hello.o, it is basically a binary file where human beings or programmers cannot make any sense out of it, because we cannot read and understand binary files, right? So but yeah, the input to assembler is a assembly code, that is hello.s, and this hello.s, when given to assembler, will convert this assembly instructions into the binary code, okay, which is which you basically call it as object code. But keep in mind, this binary code is not the executable file. Okay, the CPU is not ready to execute this. I'll tell you why in a little while later. Okay, for now let us practically see this. Let me recall this assembly stage once again. The assembly stage is taken care by the assembler. When I say taken care, assembler will do the assembling part and converts assembly code into object code. This is the object code, right? Hello.s. This is the output. So input is hello.s, okay, and the output is hello.o. The output is hello.o. So, okay, so the input that you give to the assembler is hello.s, and the output that you get is hello.o. Okay, so how do I actually find this hello.o? Okay, by using the command cc minus c and giving hello.s as the input to the assembler, right? So hello.s was the output of the actual compilation stage. You can see here hello.s was the output of the actual compilation stage, and this output is now given as input to the assembler, so that we get a new output file called as hello.o. Okay, so we are supposed to get this. Let us see this using the command cc minus c hello.s. Let me try this out in a terminal. Okay, so as you can see here, we have hello.c, hello.i and hello.s. Now I'm going to do the assembling by saying cc minus c and passing it as an input hello.s, that is the output of the previous stage, that is actual compilation stage. So when I press the enter key, okay, I can see that there is one more file that got generated, that is hello.o, which is nothing but the object code. It's a binary file, we cannot make out anything out of it, okay, but let me still show it to you. It looks like this, it's completely jumbled up, we don't understand, it's a binary file format, okay. So let us not try to make more sense out of it, because we might not be successful in making out anything in this, okay. So this is basically hello.o, but yeah, so though we have got a binary file, this is not executable file. Okay, the reason is that it has certain missing informations. It has a lot of missing stuff. So what are those? As you can see in this program, right? We have something called as puts hello world, and in our program we have printf hello world. As you can see, let me show this. Okay, hello.c. Okay, we have something called as printf hello world, right? So this is basically a function call, and we need a function definition for it to do this activity. Okay, we need a function definition, but where is the function definition? The function definition is present in the library. It is present in a library, right? Okay, so printf's function call is there in this particular file, but printf's function definition is there in a separate file called as a library, right? libc.so. Okay, let us not bother about what does so stands for. It basically stands for shared object, but you may not understand when I talk about libraries for now. But just one thing that you got to understand now is that we have we have some external files called as libraries, which will contain some predefined functions for the calls that we are using in our source code, right? So hello.o does not contain the definition, right? So there must be someone who can actually link those function calls to the function definitions that are present in the library, and the one who actually does that job is the linker, right? So that is the final stage, the final step. So linker will take this hello.o, okay, as input, and it would actually link the external libraries, and it will fill the information, missing information, to hello.o. After doing the linking of this library, okay, it will generate another binary file which is called as an executable file, which is ready, which contains all the information for the CPU to run the program successfully, and that executable file is called as a.out, which happens during the linking stage. That is the final stage, right? So now let me just explain that to you here using a slide. So the linking stage, the linker takes care of the linking stage, fills missing information in the object code, and produces the final executable file. So this is basically the final executable file, okay. Though it does not look like this when I open this executable file, but just for the pictorial representation I have given you over here, okay. So this is a.out, right? So if I want to see how what happens, or how to generate a.out file, okay, then the command used is cc minus o a.out hello.c, right? So let me run that executable and show it to you. Let me show that practically to you, right? So as you can see, there is no a.out for now over here, okay. It is hello.c, the original source code, and hello.i, which I actually got after the pre-processing stage, and hello.s, which we got after the actual compilation stage, and hello.o we got after the assembly stage. Now let me actually try to do the linking. It is cc minus o, the executable file is a.out, and then let me give the input as hello.c, or you can either give hello.o, both are fine, okay. So and then press an enter key. The moment I press an enter key, you can see that my final executable file is ready, a.out. So when I try to open that file and try to see its contents, absolutely not possible to make out any information, because I'll not be able to make any sense out of this, because it is completely a binary file, okay. And so the way it is different from your object code and from and a.out, the difference between your hello.o and a.out is that both are binary files, okay. But hello.o is a binary file which has some missing information, like the function definitions, or all such kind of stuff, which would be filled by the linker, and it would be linked together, and then it will produce your final executable. So your final executable a.out is a binary file which has all the information ready for the CPU to execute, right? Now, so after performing these 4 stages, so we are ready to run our C program. So let me run the C program by saying ./a.out. Okay, so before that, let me see what is the output that it is supposed to generate. Okay, so it is supposed to say hello world, right? So let me see if I run this executable, will I be able to get that output ./a.out. Yes, we are successfully able to get the output, desired output, hello world. Okay, so these are the four stages of your compilation process. So to repeat, so compiler to convert a high level source code into an executable file takes four steps or four stages. The first stage being pre-processing, taken care by the preprocessor, which will do the textual replacement, right? And the input given to the stage one is a source file hello.c, and from hello.c, okay, it does the textual replacement, it expands the source code and gives us the output file hello.i, which contains an expanded source code, and this expanded source code is given to the stage 2 where the actual compilation happens, done by the C compiler proper. So he will check for all the syntax errors, okay, he'll check if the vocabulary of the language is right, if the keywords used are right, and if he finds there is no problem in this particular file, then he will convert that into an assembly code. If suppose he finds any error, he throws an error immediately stopping the further process, right? Now, if there is no error, he converts that into an assembly code called as hello.s, which contains assembly instructions. But because our CPU doesn't understand your assembly instructions, so we need an assembler which will convert your assembly instructions into binary code. And the binary code, okay, is called as hello.o. It is basically called as an object code, okay. So this is not an executable because it misses certain information needed for the CPU to execute the program completely. And one of the missing information is the function definition, which is not present in our file, and the standard function definitions, that is the predefined functions, are there in the library for standard functions like printf, scanf, putf and all such kind of stuff. It is present in a library called as libc.so, or it might be in some other library, and that library has to be linked during compilation steps, so that the CPU will be able to execute your program successfully, and that job of linking is done by the linker, right? So after performing the linking operation, the linker would finally give us the final binary file, which you can call it as an executable, which can be easily executed by the CPU, and that is called as a.out. On Windows machines, okay, you will get an extension, a file with an extension .exe. Okay, I have just explained it with reference to a Unix machine. So these are the four stages of C compilation process. So first one is pre-processing, second one is actual compilation, third one is assembling, and fourth one is linking, right? So I hope you understood these four stages of compilation process in detail. So if you have any doubt, you can actually post your doubts in the comment section below, and I would be able to, I'll try my best to answer all your questions. Okay, and thanks for watching this video. Meet you in the next video. Until then, take care. Bye bye. See you.